Hello everyone, my name is Harshita Adlakha and I am a research associate in the Blue Marble Space Young Scientist Program mentored by Dr. Jen Palang. Today I am excited to share my research with you. We built a computer model to answer a simple important question: what happens to life support on Mars when we factor in a daily reality of human tiredness, stress and workload? So here is a quick look at what I will cover today. The background of this project in the Young Scientist Program, the why traditional planning models miss human factors, how our model works using real Mars roam data, an important mistake I caught and fixed in my own numbers, our final summation results, and the key takeaways. So this work was done as a part of New Marble Space Young Scientist Program, which gives early career researcher hand-on experience with space science. My internship had two main stages. First, we designed a 100% base inside a Martian lava tube across 8 functional areas. In the second stage, I turned that agriculture design into a dynamic simulation to test how resilient the habitat really is during a long-term emergencies. So here is a quick look at what we actually designed. On the left is the underground farming century using a Martian soil inside a protected lava tube to grow fresh fruits. And on the right side is a living suit designed to keep crew members healthy and comfortable during a long multi-year stay. These designs gave us a real operational numbers we used in our computer model. So our model brings together three fields of research that actually stay separate. First is the living support engineering, which look at total resource numbers like oxygen and water, lava. Second is the lava tube studies, which focuses on radiation shielding and constructions. And third is the extreme environment psychology, which studies how isolation causes crew stresses and fatigue. Our model connects all three into a single system. So normally, space mission planners uses static budgets like a fixed checklist of a supply. The problem is that the real life does not work like a static checklist. Over a 2-year mission, equipments break down, repair piles up, and the crew members get tired. So when a crew member is exhausted, repair slows down, which means life support recycle less air and water. That creates even more stress. So we built this model to see if the chain reaction could cause a base to fail. So we modeled a 100% crew living in a lava tube for 730 days to 2 full years with zero supplies from the earth. The model tracks two things at the same time. First is the physical resources like oxygen, water, power, and recycling rates. Second is the human factors like repair, backlogs, daily workload, and the crew fatigue. So here is how those two connects together. First one is the maintenance erosion. So when machine breaks, the repair backlog goes up, workload rises, and crew gets tired, and tiredness works fix things slower, making the backlog worse. Second is the confinement conflict. High workload make teamwork harder, and which led the team conflicts and more stress. Third is the recreation buffer. Resting and using shared recreational spaces helps the crew recharge and which keeps the whole base stable. So instead of testing made up prices, we tested the base against a real disaster, the 2018 global Mars storm. We took the real atmospheric data from the published science paper and combined it with the solar power loss formulas tested on a NASA InSight lander. This means our stress test is grounded in a real Martian condition, not the guesses. So before looking at the results, I want to share an important correction I made to my own work. Earlier, I used a placeholder number assuming only 8% of the crew worked on the maintenance. When I simulated the dust storm along with the crew illness outbreaks, the model predict and total collapse. So, however, when I went back and verified our actual week 10 habitat design, the real allocation for engineering and maintenance was 18% of the crew, more than the double. So when I put the verified 18% figure into the simulation, the collapse disappeared completely. So next is here are the results across all the tests. the normal days, the storm days, and the dust storm with crew illness. So in every scenario, the base survived safely. Life support recycling dropped slightly during the peak of the storm, but fully recovered within the roughly 100 days. So crew fatigue stayed well within the manageable bounds. Because we don't have any real human psychological database from Mars set, so we tested that would happen if our behavior assumptions were off. We swept all coupling values from minus 15% to 400%. Even with those wide variations, the habitat consistently recovered on its own. This proves the system safety does not depend on the lucky or fragile numbers. Our main headline is a positive. So, Habitat Design is generally resilient, dedicating 18 out of 100 crew members to engineering and maintenance, provides enough safety cushions to survive the largest dust storm on record and sick crew at the same time without triggering dangerous failure loops. Traditional planning only answers how many kilograms of supplies should we keep in a rocket. Our dynamic model answers can our crew and machine handles combined emergencies over a year of operation. This gives mission planners a practical way to test to long-term safety. So this is my week 10 workforce chart taken directly from the design. We can clearly see 18 crew members are assigned to the engineering and maintenance. So using this verified design value is what proved our habitat can withstand extreme stress. To completely clear about the limits of the current model. So first one is the low supply stocks do not yet feed back to trigger to panic in the code. Second is the human behavior. Numbers are tested across wide ranges and not measured directly on the Mars. Third is the model is scoped to 100% over 2 years. Other parameters should be re-verified against their original sources. So I want to say a heartful thank to you, Blue Marble Young Scientist program, and especially to my mentor, Dr. Chen Plank, for her support and guidance throughout this project. Thank you, and I will look forward to taking your questions.